can see and hear you.
Okay, fantastic. Okay. And you can see the screen and everything. So, should I go?
Yeah, so our next speaker is Carlo Rovelli, speaking about why causation is a thermodynamic and statistic phenomenon. Carlo, the stage is yours.
Wonderful. So thank you very much. Let me start by saying that I'm very sorry of not being there, not just for just listening to the talks and it's easier to give a talk directly, but also because there are a lot of people there I would like to talk directly, and I have a question I would like to discuss with them. So apologies, I really could not come, and I try to do my best with what I can offer with this talk. This talk is a little bit slightly different in tone with respect to several of the conference. Even if it is on the same issues, I try to contribute, to give a contribution on the foundations of, about the foundations of things which are being discussed. Because I find that not that anything which is said is wrong, but I do find that the notion of causation, which is widely used in this conference and among the people that I sort of see on my screen sitting there or listening or talking, I find that the notion of causation is used in an ambiguous manner. And I think that this creates conceptual confusion. So I would like to contribute by bringing some clarity about the notion of causation itself, because I think it's important, especially when we talk about non-trivial causal order. As long as we are Minkowski or even non-relativistic space-time, there's a sort of trivial time evolution. We can easily mix up notions without difficulty, but since it is an interest for many people here to look about causal orders in some little more wide way, I think that some clarifications are needed. Now, causation means a lot of things and is used in a variety of manners, but I want to focus on a distinction which is crucial, I think, for what is being discussed here, between two notions of causation, which are completely different. Of course, they are related to one another, they're connected to one another, and sort of they talk to one another in interesting manners, and this is interesting, but they're completely different. And I just call them, the nomenclature is not standard, but that's here, I think it's might be helpful to give names. One is what I would call relativistic causality, and I'll spend some time to discuss what exactly it is. But roughly, it's the fact that in the physics, modern physics, contemporary physics, so 20th century physics and 21st century physics, we know that observables can have, in fact, most observable, if not all observable we're interested in, have localization in space-time in some sense, and space-time region can be causally connected or not. In a precise sense, in relativistic physics and in classical generativity, and also in wider cases, we say that they are causally connected if there is a time like borderline in space-time that intersects both regions. If not, we say they're not causally connected, they're causally disconnected. And I want to stress that this notion, whatever you turn it around, doesn't distinguish the past from the future. It's time reversal invariant. If A is causally connected to B, B is causally connected to A. A separate notion, and it's essential to keep the two separate, is agential causality. And this is far more subtle and requires a bit more of discussion. I will discuss both of them in the next slides. But the second one is it's the notion that captures our idea that A is a cause of B, or that we can do something at A which reflects on B. So in particular, we can signal from A to B, right? That's one. In order to signal from A to B, it must be the case that if I do something on A, this causes something in B. So what happens in B depends on A. And that's a notion which is agential causality, which is oriented. A signal to B in space-time, sort of generically in our experience, also implies that B cannot signal to A. I can send a letter to tomorrow, but I cannot send a letter to yesterday. So this is definitely a non-time time-oriented notion of causation, unlike the previous one. And the relation between the two, the articulation of these two, it's very interesting and is important. And this is where I think there is confusion in the field. So let me describe the two a little bit more cleanly, and then go into the main point which I want to make. So relativistic causality comes about in modern physics. It does sharpen an intuition which was existing in pre-Einstein physics, but in post-Einstein physics, it has a very clean way of being expressed, which is careful the following. It is true in special relativity and general relativity, and it's considered established by all physicists interested in fundamental physics today, the following fact: that if there is a space-time, then the equations of motion, let's talk classically first and then quantum mechanics. The equations of motions are such that on a space-like surface, this horizontal line at t equals 0, so on a time equal constant surface, data can be given largely arbitrary, but if you know the data on a compact region R, so it's a compact part of a t equal constant surface, then the data there determine uniquely, namely they are compatible with only one possible set of values of the set of configuration of reality in the future domain of dependence, which is this triangle here. This 45 degrees is a ray of light, the speed of light is 45 degrees, in the future and in the past. And that's crucial. So if you know the value of the state of the universe on the region R, relativistic causality implies that there's only one and only one possibility for the state of the universe in the future domain of dependence and the past domain of dependence. Both, I insist on this point. What this has to do with causality? It has to do because if I have two sets of data on t equal constant that differ only on here where the letter A is designed, but not on R, then two sets of data which differ only on A necessarily do not differ in B nor in B prime. Which means that if somehow I can consider two cases with A something and A something else, this does not affect B, nor does it affect B prime, right? So A and B are causally disconnected. This is what is meant by causally disconnected in fundamental physics, fundamental relativistic physics, in classical relativistic physics, in quantum relativistic physics, in quantum field theory, and so on and so forth, okay? So the physics of B and B prime determined by two sets of data on a t equal constant surface that differs only on A on this t equal constant slide necessarily is the same in B and in B prime. Notice that there's no time direction here, and this is what relativistic causality it's about. In quantum field theory, I've changed what is written down here. The operations in quantum field theory, operations are connected to observables, which are localized in space-time. That's the core of quantum field theory. So this translates into the fact that the operators in the Hilbert space that correspond to operation in A and operation in B commute, exactly in the same sense in which operation in A and in B prime commute. Okay, so this is relativistic causality. And let's go. So let me stress once again that relativistic causality is not time-oriented. Okay. Now let's go to the other causality, which is agential causality. The one I said is more subtle. This is definitely time-oriented. And what is it? Let me, in a slide, summarize and a little simplify, present a little bit of schematic version of a discussion of what we mean by cause that has gone through and has been extraordinarily fruitful, both conceptually and technically, and has continued, I would say, for 3 centuries, because with step by step, slowly understanding causality better and better. It's important because unless we get stuck in this 16th century, we don't get clarity about these things. So let me start. I've summarized it by putting four steps. It's a little bit schematic. I mean, the reality is a little bit more complicated than that. But I think this gives the advances, what was understood. So let me start with David Hume, back in the Renaissance. Hume notoriously questions the naive notion of causation, saying that is ill-defined, and try to make sense of the everyday notion of causation by saying that it's what we call causation is nothing else than correlation. Okay, so when we say that A is the cause of B, we only mean, according to David Hume, we'll see that is wrong in a subtle sense. We only mean, according to David Hume, that every time that A happens, B happens. Every time that B happens, A happens. In other words, in our experience, we find that A and B come together. So every time we see E, we infer by induction, we expect B, and that is what we say A causes B. That was David Hume characterization of causation. David Hume is a little bit more subtle because says causation is not A and B being correlated. It's what happened in our mind. That by seeing A and B repeatedly, this coming together in our experience, we develop the expectation that after A comes B. So it's for David Hume, causation is in our mind. That's less important. The key important point is that for Hume, causation is just correlation, things happening together. And therefore, in particular, the distinction between cause and effect, it's known. There's no distinction. We call cause only the phenomenon that happened, the process that happened first, and effect that happened later. So cause and effect means only that two things are correlated, and the earlier one we call cause, the later one was effect. That's Hume. Russell, a couple centuries later, less, along the same line, but at the light of the success of classical and modern physics, make the same point but much stronger, founding it on fundamental physics. Russell is very strong in saying that causation is not a scientific notion. In fact, Russell is famous for saying that causation is a folk notion that will disappear from science, has no role in science. Because in fundamental physics, there are no causes. And in this, Russell is exactly right. There are no causes in fundamental physics, in fundamental classical mechanics, in fundamental quantum mechanics, in fundamental quantum field theory, in fundamental standard model, general relativity, quantum gravity, my field. There's no notion of cause. What is there? Well, there are laws that express observer regularity, constraints of what can happen. And these do not distinguish between the past and the future. So there could be no distinguish cause coming before the effect. There's just no room for that in fundamental physics. And so again, what we call cause a la David Hume is just correlation and our habit. Now, this seemed established, and in fact, many physicists, fundamental physicists, think in this term, but is wrong in a subtle way, and that was demolished by Nancy Cartwright in a book in a series of marvelous papers, in which she said, "Come on, this is bullshit. Causation is obviously a scientific notion," and she's right. Okay. Because that's what we do in science, right? For instance, I mean, we spend a lot of money and save the life of people by realizing that smoking is correlated to cancer, going to the hospital is correlated to cancer, but going to the hospital does not cause cancer, while smoking causes cancer, right? And this is definitely meaningful. Now, how can something be a scientific notion without existing in fundamental physics? Well, there's no contradiction between Russell and Cartwright. Careful. I mean, cats are real, but they are not in fundamental physics. So there's a lot of things which are in the world which make scientifically sense, but it's not directly captured by the notion of fundamental physics. They just come about because the world is complicated and we have proper notions for doing science at higher level. So Cartwright is right. So if she's right, what exactly do we mean by causation? Well, Cartwright herself started clarifying time lit not little, and there was a lot of discussion, and there's a beautiful set of work, including mathematical work, which I would say in its best version came into the idea of causal modeling. The image here is Judea Peirce, who wrote a very influential book and has a very clean understanding of this, in which we clearly understand what we mean by causation in physics, why smoking causes cancer. It's super useful because it's what we need in science, to, in particular, to diminish the people die by cancer by just telling them stop to smoke. We have the clear foundation of the notion of causation. And that's the second one, not the relativistic one. It's nothing to do with the relativistic one. It's the agential. So how is this, at the light of this work, the intuition by Cartwright and the work by many, including Judea Peirce, what is causation? Causation can be defined, in fact, can be rigorously defined mathematically, if you're just given the correlations, out of the correlations. So correlations are there, but in addition, there is a notion of causation, which is based on a notion of intervention of external agent assumed to affect the future and not the past. So many of you know how the logic of causal work modeling, you assume to have a certain number of variables, which is important to think that they are some of the variables of the universe, not all the variables of the universe. So there's a coarse graining here. There's else that happen in the world, but we have some information about the probabilistic correlations between that, empirical or based on some of our fundamental theories, so quantum mechanics or whatever. So there are probabilistic correlation between those, and out of those we come out from the correlations with a notion of causation. How? By playing the same game, by taking the probability relations that we have between this variable, by imagining that there is another system, an agent, which is just a physical system that acts on one of these nodes, and by artificially forgetting the correlations in the past of A. So this only works if we have a notion of time, and these are time-oriented. Judea Peirce is completely straightforward and acting clear. So if there's a notion of time, if there's an agent, if this agent can act on A, and if we assume, okay, that the world is such that this action can be irrespectively on the past effect. So H can act on A without affecting E and G. This is not a result of the probability. This is not a result of the causal model calculation itself, is an assumption, okay? Then you can say, out of the calculation, you can draw these arrows. And these arrows, with respect to all the things that happen in the future of A, distinguish those that change depending how H affect A, like F and C, and those that do not change, like B. So here you say that C and F are causally correlated to A and B is not. And this is a notion of causal agency, okay? So very importantly, in causal modeling, the notion of cause is well defined, but assumes an external intervention that assumes that the intervening agent does not affect the past, but it affects the future. Now, two questions I have to worry. Can this assumption be realized in the real world? Well, of course, yes, right? We can just affect the future, not the past, and we can affect system. We have a set of system. We come there and we do something. So they can really obviously be realized, these assumptions based on Peirce and others causal model. So it's coherent with the universe. Now, question: how can it be coherent with fundamental physics? This seems harder because fundamental physics is not time-oriented. So where does the time orientation of the agent and of the assumptions of the causal modeling logic come from? Why the agent affects the future and not the past? Okay, which is an input in the causal modeling. Careful, which is an input in the causal modeling mathematics. Given that the fundamental physics do not allow that. Well, it's not too hard because the world is full of time non-oriented thing. So where does this non-orientation come from if fundamental physics is it's time reversal invariant? Well, to do that, let me very rapidly fly through the arrows time of our experience. There is a thermodynamic arrow of time, right, which we do understand. It's not controversial. There are open questions, but I'm not going to the open question. Open question is why entropy was low in the past. Forget it. we live in a world where entropy was low in the past. There's epistemic arrow of time. Remember, we know the past. We don't know equally well the future. The agential arrow of time, the one we are focusing here, we can act on the future, but not on the past. There's a measurement arrow of time. A record of a measurement exists after the measurement, not before the measurement. And there's a quantum measurement arrow of time. Each quantum measurement is always dissipative in some sense. When we model in a laboratory something which is not unitary, we're essentially putting there a little extra system in which information is lost. So there is some dissipation, there is some order, decoherence, depending how you think about that. So there's an arrow of time there. And our thinking has an arrow of time. How are all these related? Where is the origin? Which one depends on the other here? Let me fly through them. The thermodynamic arrow of time is given. It's a fact of the universe, which comes from the two points. First, it regards the macroscopic variables, doesn't regard the micro description of the system, regard the macro description of the system. And it depends on the contingent fact that we live in a world where the macro state of the universe is has an entropy gradient, was lower entropy in the past. Take this for granted. This is a fact of our description of the world and a fact of the world around us, that we live in an entropy gradient. Now, this is the key point, because this slide is a key point, because everything else, in a sense, depends on this one. The epistemic arrow of time, we know the past better than we know the future. Where does it come from? I mean, why do we know the past? Well, it can be shown and it can be proven rigorously in, this is a paper where I discuss it, but I actually discovered that the basic ideas have been there since the 50s. And if you read the Reichenbach book, The Duration of Time, they're already there in a complicated, confused way, but they're already there. So the point is the following. If there is a thermodynamic arrow of time, then there's an epistemic arrow of time. Namely, it is a fact that the macroscopic world has a large number of traces of the past and not analogous traces of the future. It's not just us remembering the past. It's not a mental thing. It's the world. I mean, in the moon, there's no epistemic. There's nobody who learns anything, but the craters on the moon know about the past impact of meteorites, not about the future one. So the present knows about the past, not us. The present knows the past more than it knows about the future. It knows about both, but macroscopically it knows more about the past because there are traces. And now, this is the key point. It can be proven that a generic physics system with an entropy gradient is not efficient, and long-term realization time between subcomponents, which is a situation of universe in which we live, naturally generate traces of the past. In fact, naturally generates abundant traces of the past. I'm not going to go through the actual argument of that. Look at this paper or take the courage to read the Reichenbach book. But the point is that the epistemic arrow of time is just a consequence, a physical consequence, that the theoretical physics can understand why, of the thermodynamic arrow of time. So much so that the information contained in traces in memory can be bound by thermodynamic quantity, which make totally clear that it's a thermodynamical thing. In other words, every time you store something in a trace, you can do that only by raising entropy. By paying a price in terms of information, you put information somewhere, you gain information macroscopically. By losing information, namely raising entropy in the microphysics, and the amount of information can be bound, this is proven in my paper, in terms of purely thermodynamical quantity, which are temperature, heat capacities, and thermalization times. Good. The agential arrow of time is the same story. So a system, macroscopic system, can branch the macro history. This is the history of the world. It can go this way, this way, this way, depending on the process here. Is it possible? Is it compatible with determinism, with quantum mechanical probability? Yes, of course, because this is a macro system. So there are many micro possible stories compatible with it. Some goes up, some goes this way, some goes this way. You can have a system that decides, like our brain or like any machine that decides, if it generates information, if it chooses something, okay, it creates information, and is necessarily, this is a theorem, to do so, it has to raise entropy. Okay, because information cannot come from nothing. It comes from raising entropy, for eating up the negative information, which is in low entropy, right? So necessarily, agency is the thermodynamic process. This is the key point, okay? So the thermodynamic arrow of time underpins the agential arrow of time. This is, by the way, Belilo will come with exactly the same argument in a 2020 paper, which is this one, coming from a different direction. Now, rapidly, the measurement arrow of time is a case of the traces. Because every time, this is, I mean, it shocked me when I read it recently, in fact, in Reichenbach, you cannot measure classically, okay? Any measurement apparatus is necessarily dissipative. There's no way you have a machine, you get a record of something, which is a measurement of the system. There's no way to do that in a reversible manner. Necessarily is dissipation. Why? Well, because there's a trace of something happened. You have to record, and because of the previous theorem, this is dissipation. So classical measurement is necessarily a thermodynamic thing, which also means the statistic. The reason you believe that your measuring apparatus actually tell you the truth about the system is only because you have a past low entropy. It's statistic. There's no way to do that. There's no way to model that in purely mechanical terms. And this, to me, brings a lot of clarity to the same problem about quantum measurement. The same slide with quantum measurement happened. It's a big deal that quantum measurement imply reversibility, but it's not such a big deal because classical measurement imply irreversibility equal. So the measurement arrow of time, both classical and quantum mechanical, are just side effects of the fact that there's an entropy gradient, okay? And thinking requires an entropy gradient. And this is why it's so hard for us to conceive a world in which there isn't a unique time direction to evolve. But we shouldn't confuse the intuition that comes from the fact that we are animals that swim in an entropy gradient. We are created by the entropy gradient. But we shouldn't confuse that for something fundamental and not thermodynamic, not statistic, because entropy gradient is a statistical phenomenon. There's nothing, there's no rule there. It's just probability. It's just improbable that things don't happen in a reverse order of time, right? It's very improbable, but only improbable, not in the thermodynamic sense. It's a statistic sense. So I'm going toward the end. You see, in order to talk about causation, that's the key point. Agential causation, the time-oriented causation, the only way, and careful, the only way to make sense of causation, not in the time reversal one of relativistic physics, but in the agential one, the signaling one, the effective one, the cause, the one that corresponds to our notion A is the cause of B, but not vice versa. That only makes sense if we assume an external intervention which affect the future and not the past. And this, it's a good description of the world only because there's an entropy gradient, okay? Only because thermodynamic. So all the arrows of time are all variants of consequences of the same thermodynamic arrow of time. Why is it important? Because now let's go back to the set of variables that affect one another. If in the universe there are closed time-like curves, does this imply logical inconsistency? No, not at all. Because closed light cones have to do with the relativistic causation. Relativistic causation doesn't know anything about the direction of time, doesn't know anything about sending metal to itself. It only knows about where there are operations that commute or where there are no operations that commute, okay? So if there is a closed time-like curve in the universe, which very probably there is, because there are black holes in the universe, and very likely there are closed time-like curves there's no logical inconsistency annexed to there, okay? Fundamental physics is not time-oriented. But agential intervention, can it act retroactively along a closed time-like loop? Yes, in principle, but no probabilistic, because it needs an entropy gradient. Remember, entropy is probability, okay? And a gradient, very simply, a gradient cannot uniformly grow on a loop, because ds cannot be constantly zero, constantly bigger than zero along a loop, because s must be should grow and should be cannot jump. Okay, so for instance, imagine this in sort of a W matrix scenario where this represents quantum laboratories where there are operations which are performed, which are not unitary operation, which are measurement or whatever you want to call more general operation. If they are not unitary, we understand them. They are just unitary operation plus a little system there where information can go in. How you call you guys an ancilla there, or the coherence going on. All thermodynamic notions, right? Throwing away information. So could it be that there is a loop, a causal loop from A to C to D to E to A? No, if you fold in thermodynamic. No, if you remember that there is an entropy that in order to send a signal to A to C has to grow from A to C, have to grow here, to grow here, to grow here, but then it cannot go because it was lower. So in other words, do not confuse the time of the system, okay, which says which things are correlated to one another. The equation of motion or the dynamics correlate things and does not correlate other things, with the time of observer, which is in the laboratory, a guy with a memory which dissipate entropy, and therefore it's oriented. Okay, signaling is a notion. The signal orientation is a notion that requires thermodynamics. So conclusion. And this was, if you remember exactly the title of what I say, causation is the time-oriented phenomenon that can only manifest itself in a statistical framework. There's no causation in fundamental physics, if you want, in general causation. Only when we disregard microphysics, we trace over stuff, we allow reversibility, and then we get traces, so we get future-oriented agency and a notion of causation close to our intuition. We live in a world with a dramatic entropy gradient, so of course our intuition has digested all that. Causation is a statistical phenomenon which is rooted in past entropy. So thank you very much. I stop here because I think I can leave some time for question. I believe I expect many. And let me just take down just 1 second. I want to take down that strong light that is coming on me.
Could you check if the mic is on? I think the online audience could. Or maybe try this one. This seems to be...
That is better, yeah. Okay, I'll start in the middle. 24, okay.
So in your approach of this unusual, so you are saying that causation in the causal model is basically the same thing as sending a signal. But as far as
No. No, I've never said anything like that. I said that sending a signal can be interpreted a very special case of causation. It's not the same.
Yes, but what I rather mean is that actually it might be the case that you have some kind of closed causal loop inside your causal structure, which due to some fine-tuning between the correlations is not actually detectable as a signaling loop. And in this case, if I understand correctly, it wouldn't be ruled out to have a causal loop like that due to the signaling entropy gradient, right?
I haven't understood. Can you repeat? There's also the sound is not very good. Can you repeat what you were saying?
So if you have an unfaithful causal model where you have causation, where you can have signaling along the where you can actually have causal errors which you cannot detect immediately through signaling in an interventional model, then it might be the case that you have a causal loop in your causal structure, even though you can, which you can possibly certify using signaling, but where still the signaling does not go, let's say, along the causal structure. So I was wondering whether such cases you might still have loops in your causal structure even though this entropy gradient exists.
The sound is very bad. I get one.
Should we walk up to
2 words out of 3? So
okay.
your question. So I think you're asking me. First, you're saying in my construction. I don't understand what you mean by my construction.
Excuse me.
I just. But my point was try to show where the orientation of signaling come from. That's what I would try to do, and I argue that the orientation of signaling comes from something which is assumed independently in the causal model themselves, which has to do with the entropy of the agent assumed in the definition itself of causation. I've not talked about signaling in any technical sense, if not by saying that to the extent in which signaling is not time reversal, the signal is time oriented, is it itself only meaningful in a situation with an entropy gradient. And you probably asked something more technical, but I couldn't get what it is. Sorry.
Okay. So,
maybe somebody help me.
Well, I would just suggest that from now on, people come down here and ask the question here at the laptop, so that for the reason of sound. Are you satisfied with your answer, or do you have more to say to it?
Yes, for now.
Okay, then please just come down. Maybe I have to say. Okay, I guess that's the first.
I hear a huge amount of echo, so it's very, very unclean, the sound. Sorry.
We're trying to fix this.
Hey, can you hear me?
Oh, this is much better. Great. Great. Okay. Yeah, this is something. Yeah, you started by saying this going to make you happy. Yeah, this makes me happy. Exactly. I would translate this in my language by saying that what the quantum causal model that you refer to does is to capture a notion of causation, which in a more general setting, it is an extension of the kind of causation which is the one that I called relativistic causation, and not the one that I called agential causation. So it doesn't require the existence of an external intervention of an agent which necessarily a priori distinguish the future from the past. So I see no reason this not to be possible, and I'm very happy if this can be done cleanly. I guess just to add one question, my entire talking is sort of rhetorically against the idea that there is a notion of causation which is necessary at the foundation of physics, which is necessarily time-oriented. Hey, hi. Yeah, this is a deep question, Czaslaw, and I think I see where you come from and where you're going, and I have two comments exactly in this direction about how physics is formulated. One, and actually they're both crucial in my opinion. One is that physics is modal. Namely, physics is not about how things are. Physics has never been things are like that. Physics, both quantum and classical, is modal. If this, then that. If you do this, you see that. If you see this, then you see that. If you see, and classical physics, it's very clearly modal. You know, the modality in classical physics is the initial data or the phase space, or the set of solution of equation of motion. If you describe a pendulum, you write an equation. This equation doesn't describe how the pendulum moves. It describes how the pendulum can move. So the motion that you actually detect in the pendulum is one of the possible solutions of the equation of motion. Now, the modality can be given the initial data or the final data or intermediate data or one initial moment or one initial position, one final position. Classical physics does not distinguish what comes first. I believe that it's the same true in quantum physics. Namely, quantum physics works in the same manner. It's strongly modal. It's if this, and the if, the premise, and the consequence work in both ways. Namely, if I'm given a set of measurement by a laboratory, quantum mechanics, I can test whether they satisfy the quantum theory, the theoretical quantum theory I'm given, both by taking the final, the later result as if, or taking the earlier result as if. That's the first point. So yes, quantum mechanics is it's formulated in terms of choosing an alternative, but so is classical, and this has nothing to do with time reversal invariant. But the second point is stronger. We always describe, in my opinion, and I would expect you to agree with that, not the universe as a whole, but a part of the universe. Okay, quantum theories describe always a piece of the universe. I think a piece of universe can be in a large-scale structural universe. One can do quantum cosmology, but it's still a subset of the possible degrees of freedom of the universe. So when we describe quantum physics, we always describe, or classical physics, how a system behaves from the moment it interacts with something and the moment it interacts with something else. So between interactions. And in any description, we disregard, we give the other system as arbitrary. If the other system is doing this, something happened. If the other system is doing something else, something else. For instance, if I describe the geology of the moon, I consider the meteorite as something external, and I have, in my equations, the possibility of choosing a meteorite coming down or not coming down. And as you say, and I think we agree here, nothing is anthropomorphic here, but there is a notion of external agent, which comes into the core of the distinction between measurement and state in quantum mechanics, because the measurement has to do with what the other system is coming in and the interaction Hamiltonian between the other system. And once again, I think that this is true. I'm 100% with every word that you say. I don't think that in this there is anything time-oriented. Namely, the fundamental formulation of quantum mechanics, it's time symmetric with respect to the input can be before, later, a little before, a little bit later, or even in the middle in some sense. So I'm not questioning at all neither the modality of the theory nor the fact that the formalism requires an external something to doing something to the system. My only point is about the connection between these things and the direction of time. And my point is these things are compatible with both in non-relativistic physics going ahead or backward in time, and in a more general situation, we should not confuse these things, which are essential for understanding how we think about quantum mechanics, with the issue that signaling goes to the future and not to the past, which is a totally different story, and comes in only because we were making some assumptions about the other system interacting with the quantum system we're describing. Thank you. Sorry for not being there. And at the panel, I'll have nothing to say. Only answer your questions. So.
That promise. Let's conclude this session and thank Carlo once more, and then go for lunch.